Welcome back to Low-Level Programming Crashcasts. I'm Sheila, and I'm here with Victor to dive deeper into the fascinating world of low-level programming. Before we start, if you're enjoying our podcast, please take a moment to rate us on your preferred podcast platform. Your support means the world to us.
That's right, Sheila. And today, we're continuing our journey through the number systems and data representation chapter. We've already covered binary, decimal, and hexadecimal systems. Now we're moving on to a crucial topic, signed and unsigned numbers.
Ooh, this sounds intriguing. But before we dive in, I've got a quiz question for our listeners. Here it is. What's the difference between the range of values that can be represented by an 8-bit signed integer versus an 8-bit unsigned integer?
That's an excellent question, Sheila. It really gets to the heart of today's topic. Listeners, take a moment to think about it. Consider what you know about binary numbers and how many different values can be represented with 8 bits. The answer might surprise you.
While our listeners ponder that, let's start with the basics. Victor, could you explain what we mean by signed and unsigned numbers?
Certainly, in computer systems, we often need to represent both positive and negative numbers. Unsigned numbers are always positive or zero, while signed numbers can be positive, negative, or zero. The key difference is how we interpret the bits that make up these numbers.
I see. So unsigned numbers are straightforward. They're just positive integers. But how do we represent negative numbers in binary?
Great question. The most common method used in modern computers is called 2's complement. In this system, the leftmost bit, most significant bit, is used as a sign bit. If it's 0, the number is positive, and if it's 1, the number is negative.
That makes sense for determining if a number is positive or negative. But how do we actually represent the negative values?
Well, for positive numbers, it's straightforward. We represent them just like unsigned numbers. For negative numbers, we use a process called 2's complement. First, we invert all the bits, then add 1 to the result.
Oh, interesting. Can you give an example of how this works?
Sure. Let's take the number 5 in an 8-bit system. First, we start with positive 5, which is 00101001 in binary. To make it negative, we invert all the bits to get 11 1 now 1 1 do 1 2, then add 1, resulting in 11 now 1 1 11. This is the 2's complement representation of 5.
Fascinating. It's like a little dance of bits. But why do we do it this way? It seems complicated.
Great observation. The beauty of 2's complement is that it allows us to perform addition and subtraction using the same circuitry, regardless of whether we're dealing with positive or negative numbers. It simplifies hardware design and makes operations more efficient.
That's clever. Now I'm curious about the range of values. How does using signed numbers affect the range compared to unsigned numbers?
Excellent question. This ties back to our quiz. For an 8-bit unsigned integer, we can represent values from 0 to 255, 2 positive 8, 1. But for an 8-bit signed integer, we use 1 bit for the sign, leaving us with a range from 128 to 127.
Wow, that's quite a difference. So we trade half of our positive range for the ability to represent negative numbers. Are there situations where this trade-off is particularly important?
Absolutely. In many real-world applications, we need to represent both positive and negative values. Think about temperature readings, financial transactions, or even coordinates in a game. Using signed numbers allows us to represent these naturally.
That makes sense. I can see how using unsigned numbers for something like temperature could lead to problems. Speaking of problems, are there any common pitfalls when working with signed and unsigned numbers?
Oh, definitely. One of the most common issues is integer overflow or underflow. This can happen when an operation results in a value outside the representable range. For example, adding 1 to the maximum positive value in a signed integer will actually wrap around to the minimum negative value.
That sounds like it could cause some nasty bugs. Do you have any memorable anecdotes about issues caused by signed or unsigned confusion?
As a matter of fact, I do. There was a famous bug in the Ariane 5 rocket launch in 1996. a piece of the guidance software tried to stuff a 64-bit floating point value into a 16-bit signed integer. The resulting overflow caused the rocket to veer off course and self-destruct, resulting in a loss of more than $370 million. It's a stark reminder of how important it is to understand and handle these issues correctly.
Wow, that's a costly mistake. Any tips for our listeners on how to avoid such pitfalls?
Absolutely. Always be aware of the data types you're using and their limitations. Use appropriate types for your data, and when converting between types, check for potential overflow or underflow. Many modern programming languages and compilers provide tools and warnings to help catch these issues early.
Great advice. Now, before we wrap up, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
Certainly, the range for an 8-bit unsigned integer is 0 to 255, which is 256 different values. For an 8-bit signed integer, the range is 128 to 127, which is also 256 different values. The key difference is not in the number of values, but in the range they cover.
Fascinating. To summarize today's episode, we've learned about signed and unsigned numbers, how negative numbers are represented using 2's complement, the range differences between signed and unsigned integers, and some potential pitfalls to watch out for when working with these number systems.
Excellent summary, Sheila. Remember, understanding these concepts is crucial for low-level programming and can help prevent subtle but potentially catastrophic bugs in your code.
Thank you, Victor, for these insights, and thank you, listeners, for tuning in. If you enjoyed this episode, please visit crashcasts.com, join our Discord community, or support us on Patreon. Don't forget to subscribe and rate our podcast. Until next time, happy coding.